Hello everyone and welcome to our webinar today. This is on flame scanners, flame detectors, and flame sensors, if you will. Today I'm going to be discussing the different types and how they're used with flame safeguards in particular. Uh, the flame scanner is truly the main component of the flame safeguard system, and making sure that the correct type is used for a particular application is really the key to making sure that we have reliable burner operation. It's not overstating the value of this component to say that without reliable flame scanner operation, many buildings would not have heat, food processing plants would shut down, and even our power utilities could go dark. So yeah, this component is about as important as any in our industry, and many times overlooked how important it really is. So in understanding how these products work and how they're applied properly is extremely valuable. So hopefully today, after we finish the presentation, you'll have a better understanding of how to apply these, how they actually operate, hopefully how to troubleshoot those, issues on how to install them properly and so forth. So with that being said, let's back up just a little bit and give you an idea about myself. I'm based out of Tulsa, Oklahoma. I've been with Preferred Utilities now for about 2 years, a little over 2 years actually. And before Preferred Utilities, I actually spent 23 years with FireEye. I started as a regional sales manager over there for a few years and then moved into the national sales manager position. That's where I really gained the majority of my knowledge on flame safeguards and spent a lot of time in boiler rooms over the years. I was brought on to Preferred Utilities to actually expand our business across the United States. Preferred has been kind of a primarily Northeast company, and we are adding partners, if you will, dealers across the nation now to actually sell our products in other areas. So you'll be seeing that on our website as we do add other business partners. My actual degree is in electronics engineering from Oklahoma State quite a few years ago. So that helps me from the flame safeguard standpoint in those applications. If you look at the flame scanner history, you're actually going to look and if you do some real research, you'll find that the optical flame sensor really dates back to the 1800s. But the first practical infrared detector was really produced in 1917. And this first practical IR sensor was really applied for military use. And they found that when they developed this sensor, they could actually even track an aircraft at a range of like a mile away. So this technology was really quickly adapted for other uses in the military, like missile guidance. And as some very smart individuals figured out pretty quick, that if this particular sensor technology, which was infrared technology, if they could actually sense this heat from those kind of distances, it could be applied to like a burner operation. And during this period of time in our history, of course, in the world history, we were adding so many more boilers out there that we actually were having boiler explosions because burners would go out, try to relight, and we would have explosions. So these individuals really looked at this technology and decided that they could actually develop a product around that technology to actually see when the flame on a burner was struggling or would go out, and they could interrupt the fuel delivery to the burner and prevent these explosions. So very quickly, a new industry was born. And these new components back then were actually vacuum tube based because we didn't have the solid state stuff. But those components, some of them, believe it or not, are still in operation today, which is quite amazing. But it just shows, you know, we had some very smart individuals applying that technology back then. Before we actually get into the flame scanner technology itself and the different types, it's very valuable to understand the different types of the terms that are used when you're talking about the Flame Safeguard product and how it responds or how it's used when combined with a flame scanner. One of the first terms is the flame failure response time, or FFRT. You'll hear this quite often. And in the industry, on most boiler applications, you're going to see this FFRT is going to be around a 3-second time period. And what that means is basically once the flame is established and recognized by the Flame Safeguard through the flame scanner, that flame, if it disappears and there's no flame signal for that particular time, say that 3 seconds, it will then remove the power. The Flame Safeguard will remove the power from the fuel valves and possibly go into a post purge, but definitely shut down the burner because we've had a loss of flame when there's supposed to be flame present. Now, sometimes depending on the size of the burner, this flame failure response time could be as low as even 1 second, but just depends on the particular application. So flame failure response time, very important. Sometimes this is misapplied, and on certain instances, there will be a flame failure response time that's picked that's too short because they feel that's safer. But in some applications, burners kind of struggle with that. So that's where you would get into more things like flame stabilization and things like that. So another term is delay on. Now this will be more applied usually to like smart scanner applications, but what you can do is you can actually set a time period in there where it will not recognize the flame until the flame has been present in a certain level for a certain number of seconds, or maybe only 1 second. But that's a term that's being used more and more also. False flame is a term that's been used for a long time, and primarily you saw it originally because of oil burners, because you would have afterburn or overburn. And so even though you've shut off all the fuel valves, you basically would still have flame present for a certain period of time. This is important to understand this, but it also can apply for gas fuel type applications where we may have a fuel valve that's actually starting to fail. It's extremely important to investigate a false flame shutdown or lockout in a Flame Safeguard, because we should not be seeing that at all. So this is very important to investigate this thoroughly. Flame failure PTFI. Okay, this is a flame failure situation where we have actually started the burner, and during the pilot trial for ignition period, our pilot's gone out. So we're going to get a lockout on the Flame Safeguard saying it saw the flame and the flame did not establish completely. So this is important. This is going to tell us that we're having pilot issues. A lot of times when I've actually been in the field and seen this particular flame failure, it's been just a case of adjusting the pilot fuel regulator and being able to just to get a little bit stronger signal there. And that a lot of times that's all that's necessary to fix that particular problem. Although it could be a situation also where that pilot is just not lighting. So we may have to investigate further. see if we've got an ignition transformer issue, or maybe even, again, maybe a pilot fuel valve issue. So this is a very good troubleshooting tool. If you get this lockout, you can start looking into just the pilot. Now, if we have a flame failure MTFI, what that's telling us is that we basically have a flame failure during the main trial for ignition period. Now, in most flame safeguard applications, the PTFI time could be 5 seconds or 10 seconds as a rule. The MTFI period could be 10 seconds or maybe 15 seconds, depending on the application. But again, if we get a failure to light or a flame failure during that main trial for ignition, then we're going to get that lockout, and this flame safeguard is going to point us toward maybe an issue with some main fuel valves not operating quick enough or correctly. There may be some issues there. Most of the time, this is, again, it could be even a flame scanner sighting issue, and that's something that would have to be investigated. So again, this is another troubleshooting message that could come up in a lockout with a flame safeguard, but it's going to be during that second period of lighting the burner when we're bringing on the main fuel valves. Also, flame failure during auto. Flame failure during auto means that we've actually got through PTFI. We've got the pilot lit. We've gone through main trial for ignition. Main fuel valves have come up. We've gone through that period, and we've released to auto. In other words, to modulation. And at some point in time during modulation, and this could be quickly or it could be after it's been running for a while, we could have a flame failure during modulation. So again, this is giving us another tool also to see what's going on. This could be caused by a variety of issues, including maybe a flame scanner is starting to fail. It could be a temperature related problem. So we just don't know. But this again tells us in that startup procedure and running sequence, if you will, when we lost the flame signal. Now, the flame signal is very important to know on the particular flame safeguard. There is really not any standard there on flame signal units. So you'll want to know from the manual, what the bare minimum flame signal is and what that range is. And so when you have an issue and a flame failure, make sure that you know what that range is. And hopefully someone took some notes when they actually started up the burner originally, and they recorded what those flame signals were at pilot and at main flame, and then across the firing rate range. If those notes are there, that's extremely valuable for someone that's trying to troubleshoot a problem. Check scanner. Check scanner usually will come up as a shutdown, meaning that it's probably a problem with the self-check scanner. And you'll see I've got self-checking there too. But when you have a self-checking UV scanner, a lot of times if there's a problem with the shutter assembly, that could trip this check scanner lockout or the self-checking lockout. So it just depends on the terminology from the particular scanner manufacturer, flame safeguard manufacturer. So these are just a few of the terms I thought would be good basics for you to understand a little bit more and understand why those could come up and what to look for, right off the bat if you're having to troubleshoot it. Wiring a flame scanner most of the time is, once it's done correctly, there's no issues with the wiring as a rule, unless there's some vibration issues or maybe some heat issues. one of the biggest mistakes people make when they're wiring a flame scanner, regardless of whether it's from the manufacturer or it's in the field, is they will run the flame scanner wiring too close to the ignition wiring, and you want to keep that separated as far as possible, because obviously in an ignition transformer, when you're actually providing that to the pilot assembly, that's a very high voltage, and we want to try to make sure that we're not actually coupling that high voltage spark signal, if you will, to that flame scanner lead. So keeping those separated as much as possible is very valuable. In wiring a UV tube self-check or non-self-check, basically about 50 feet of wiring is the most. That gets asked from time to time. The majority of your applications are going to be a lot shorter than that. Just follow the manufacturer's requirements there. Sometimes people will ask, can I extend that wire at all? You can, if it's wired correctly, and obviously put in the conduit or a conduit rate, you know, if it's rated for that area. But you can extend those, but most of the time those are going to be bought the proper length, you know, to get back to the control panel, to the flame safeguard. The infrared lead sulfide cell, about 100-foot max on that. Again, this is the IR cell is a low voltage device, so you know, keeping that shorter is always better. And again, keeping it away from any kind of other noise inducing components, very important, very, very important. So keeping those separate, you need to be there. The flame rod, if you're using that particular type of detector, about 50 feet on a flame rod is also about the max on that. Obviously with a flame rod, it's going to be close to where the spark is induced also, so that's going to be the closest that's going to be. And most flame safeguards, the designers have taken a lot of precautions to make sure that if any kind of noise from the ignition transformer is ignored by the flame rod or flame ionization detector. So that's basically some of the basics on the wiring. It is no doubt that there is some real issues out there, and it can be problematic when people run the wires in with other components that can cause noise induction. The different types of flame sensors now. There's basically three types of sensors. You have the temperature sensor, which is a thermocouple. You have direct contact. You have optical. With the temperature, the thermocouple, that's a millivolt output. What you have there is two dissimilar metals, basically, that are joined together, and that joint, actually, depending on the temperature, will give us a millivolt output. That's going to be on smaller applications, and I'll repeat this. Direct contact is going to be like a flame rod, and that's, you'll hear the term flame ionization or AC signal rectification. Also, the most common anymore for larger burner applications would be optical. This would be the ones that fall into the visible light spectrum, UV radiation spectrum, the IR area. And we also will have smart scanners, and the smart scanners in the optical realm are going to be the ones that probably are using a solid state element, and they are a bit different than your standard and most common UV tubes, but they will use a lot of times the same type of element as our standard lead sulfide scanners, but they will have processing built into them, so they are different, and we'll discuss that a little bit more in depth later. Usually with the smart scanners, that's where we have need flame discrimination, in other words, multiple burners, and maybe multiple types of fuels, where we will have a real spectrum of light depending on the different types of fuels. So let's talk about the thermocouple, or the flame scanner, or I wouldn't say scanner, flame sensor. This is something I'm just bringing up because this is what we would have in like a water heater in a domestic application. Although it's amazing how many times thermocouples are used to verify that we do have a heat process operating correctly. And there are different types of thermocouples. The most common are probably going to be the type K thermocouples. And I've put up a chart here to kind of show you what the voltage is versus temperature. And what this allows us to do is determine what that temperature is based off of that millivolt input. Again, a very, very low signal, so we have to have something that's very accurate in being able to measure that very low temperature. Again, this is primarily for domestic type applications, very, very small burners, but I did want to bring it up. Small residential burners, that's the application for these. Now, if we talk about direct contact sensors, this is most primarily going to be the flame rod. And this is a method that's used a lot of times in like makeup air applications, but it's referred to as flame ionization or flame rectification. What it basically does is in the flame safeguard itself, you're going to have the flame rod, which is usually made of a material called canthanol, so it's very high temperature resistant, and it will actually be used to insert where the flame needs to be. And one of the real advantages of a flame rod is you can actually determine where you want that flame length to be at a minimum, and therefore it's going to determine, yep, I've got flame there. What we're actually doing once that flame is established, there is a voltage applied to that flame rod versus ground. Okay, now this voltage could be 120 volts AC, it could be 300 volts AC, but what we're doing is we're utilizing the flame as a path of electrical electrical path through there. So we're conducting current from the flame rod to ground. And what's nice about this particular type of product is if we had, for instance, somehow those two lines going out to that ground and going out to the flame rod were shorted, we would be able to tell that that's a short and fault. The flame safeguard would recognize that and would actually shut down on a failure, indicating that there was an issue. Now, if it's operating correctly, and we actually start, for instance, a pilot or even a main flame, and we have the flame at the proper length into the flame rod, we basically, with that voltage applied, it is then going to load that signal, if you will. Inside the flame safeguard, it's allowing it to only load the negative, if you will, side of the actual AC sine wave. So we actually start loading that and it'll start dropping back. This is why we call it flame rectification. So we can determine that, yes, we do have a flame signal at that point and it's not a short. So it has its uses. It can be really, really effective in a lot of applications. Where are these used? Primarily in furnaces, or ovens, probably as much as any place in makeup air units, but it's used on gas pilots a lot of times, even larger gas pilots, or small to medium burners. So it has its place, it works well, and it tends to be more on the small or medium sized burner range where you will see this utilized. Now, okay, what would be the most common problems we might run into with a flame rod? Well, quite honestly, it's corrosion, or it could be even moisture. So how they're actually mounted in a burner assembly is very key to whether they're going to be reliable or not. We can get some corrosion on that. We can get some combustion byproduct buildup on that flame rod, and that can cause the resistance obviously to go up. There can also be insulator cracking. So if we have the insulator that the flame rod comes out of cracks, then we can start getting an intermittent short to ground. That can be problematic. And of course, the improper installation. What you want to see is basically about a third of the flame rod inserted into the flame and a lot less. So sometimes less flame rod in that flame is better than more. Some will try to put more of the flame rod into the flame, and it actually will bring the flame signal down. So actually watching flame signal and making sure that it falls into the range that the flame safeguard manufacturer recommends is key to making sure this is operating properly. And a lot of times, if someone has some intermittent flame failures and it's a flame rod application, cleaning that flame rod or replacing that flame rod fixes the problem right off the bat. And on the flame sensors types, on the optical side of things, we're going to have 3 different types. We're going to have the visible light spectrum scanner. We're going to have an ultraviolet light spectrum and the infrared light spectrum. And I put up the graph here just to kind of give you an idea of where everything falls into. Probably one of the biggest mistakes when it really comes to flame scanner, optical flame scanner applications is aiming them correctly. And just because we might have a fixed sight tube doesn't mean that we may be seeing all of the flame that we need. Because on most power burner applications, that sight tube needs to be able to see the pilot and the main flame and be able to see a really full view of that flame. Now, if you look at, for instance, UV, the majority of the UV produced in a typical burner flame is in the first 1/3 of that flame of that burner head. So being able to see a cross section of the base of that flame off the burner head is really, really important. And of course, seeing the pilot too. Now, one of the things that, you know, over the years that a lot of the burner manufacturers learned was, oh my gosh, there's a lot of UV produced by the spark, by the igniter. And that's the reason we'll have a lot of times they will move where that's actually located so that we do not, the flame sensor does not see that spark. Or we have basically a delayed spark or early spark termination and then check for the pilot to make sure that it's lit. So that first third of that flame on a UV or a gas burner, if you will, that's going to be right there in that first third of the flame, right off the burner head. Now, one of the things also that can happen is as we increase firing rate, that flame can actually burn off that burner head or lift off, if you will, and we may not have a really good view. And a lot of people have been kind of, you know, puzzled by, I've got great flame signal at low fire, but it tends to be going away as I go up the firing rate range. It could be that the flame is moving out of the sight view of the flame scanner. So that's something to be aware of. On the infrared, the majority of the infrared on a burner is basically generated in the top third of that flame. So it's going to be actually better aimed, more cross and toward the top of the flame itself. Now, over the years, people have been worried about seeing, or the scanners, oh, well, it sees refractory, and that's really problematic. Well, the flame safeguard manufacturers and designers decided that we need to look at the actual flicker of that flame, because every combustion process has a modulation, if you will. Okay, so, or a flicker frequency. So what the flame safeguard manufacturers did was looked at, okay, we should see a flicker frequency around, you know, 80 or 100 hertz in here. If we see something that's very slow moving, that's going to be refractory. So the good designers understood how to recognize and discriminate between the infrared scanner seeing refractory or seeing the actual combustion process. In fact, some of the best designers were able to actually dial in, ignore even stronger IR signal that's very slow modulating versus the quicker modulating IR of the actual combustion process. So these, it might seem like it's a simple process, but that Flame Safeguard is really able to recognize the difference these days. And again, if that scanner is mounted on a fixed sight tube, you've got to make sure that you've got a really good, if you're having issues, have a really complete view of the pilot flame and the main flame across that firing rate range. Okay, so we got the three different types of flame scanners: the visible light, we have ultraviolet light, and we have infrared. Let's talk about the visible light spectrum right now. Okay, that's going to be in that 400 nanometer to 800 nanometer range. That's what our eyes can see. And when it came to beyond the infrared sensors, when we were looking at other ways of recognizing combustion or flame, visible light was used. Okay, and those were used quite a bit many years ago. But it was mostly on smaller burners, and it's been basically discontinued now. And you're thinking, well, if it's a dark combustion, area and vessel, I mean, then it should be fine. The problem is if we end up getting some light in there that's not supposed to be there, you could end up with false flame from ambient light. And that was the most common problem with a visible light detector, and that's the reason they have really gone away over time. Now, if we get into the UV scanners, which are really the most common right now in our industry, you're going to see two different types. You're going to see the UV non-self check, and you're going to see a UV self check. And we'll discuss that in length later. But if you look at this particular scanner in particular, you're going to see that it has a UV tube. If in fact on the right side there, you'll see this wire, and that wire basically is one side of two plates that are in there. These tubes are actually manufactured so that there's two elements in there inside the tube, and it has a very special gas that tube is filled with. And what it is basically if we apply a voltage, and it can be a 300 volt DC or AC, it could be 600 volt AC, but we're going to then, when we subject that tube, if you will, to enough UV radiation, and these were developed so that they're looking below the visible light area. So they're down in this deep UV as a rule, in that basically 200 nanometer range, which is really great because it's not going to respond to visible light. And so what do? Well, with that 300 volts DC or AC or 600 volt AC, depending on what the designer decided to do, what it's going to do is if we get enough UV radiation in there, it's going to conduct. In other words, short between those two, if you will, inside the tube. So what it will do is load that circuit. So we will have, when we have zero flame signal or no UV there, we're going to have a full voltage, okay? And when we start conducting between those two, it's called pulses. The stronger the UV is, the more pulses between the two plates inside that tube. And that basically starts loading that circuit. The Flame Safeguard sees these pulses and determines the flame signal strength on the number of pulses that it's actually receiving. The more pulses, the stronger the UV signal. So we're able to determine very reliably that we have flame signal there. These are going to be applied, the non-self check scanners are going to be applied on small to medium gas burners or air atomized light oil burners. And here's the key: on the ones that are cycled on and off on a regular basis. Okay, that's very key, because these types of sensors, the UV tubes, over time, if they're subjected to enough ultraviolet light for a long length of time, you could have what's called saturation or a runaway tube. And that's going to be telling us we've got a flame even when we don't. So we want to make sure that we apply that product properly on an application that's cycled at least every 8 hours is my recommendation. Now, what are the most common problems with these? Basically, it's like any optical scanner. It's going to be sighting or vibration. These are quartz tubes, okay? They do have small leads that come out of those that are attached to wires. If we have a lot of vibration, we could actually break the seal on that tube, losing that particular special gas in there, and it will start conducting whether we have any UV or not. So we're going to start getting a false flame indication is what will happen because we've got a runaway tube. Temperature also. Most of them are rated up around 200 degrees Fahrenheit, but a lot of times heat soak or just, operating up there at the max for long lengths of time can eventually damage them or even damage the wiring. Most of them are rated extremely high now. We've got better materials for the wires and so forth, but it can still happen. So I always ask the questions if someone's having a problem, when does this occur? How long was it running? Was it up and running for a long period of time before you had a false a shutdown? There's some questions that can be asked right there. Okay. And age. Actually, over a long period of time, some can last, 15, 20 years. Just depends on the application itself, the temperature swings and so forth. But eventually, they will fail even from age. In the past, I've recommended that everyone keep a spare, of course, because it's such a critical component. But after about 8 years, chances are it's going to fail before long. Now, let's talk about the other ultraviolet scanner. This is the self-checking scanner. Because of processes that run, sometimes more than 8 hours without being shut off, it was determined that we needed to make sure that that UV tube was not in a runaway condition or state. So engineers many years ago decided that, we probably need to check that tube some way automatically to make sure that it's not in runaway state. So the UV self-checking scanner was actually designed. Again, it's using a tube, most of them, and it's operating in that 200 nanometer range or deep UV area, okay? And most of these, regardless of the brand, will have what's a shutter in it. And what this shutter basically does is operates off a timing circuit so that every so many seconds, it actually closes off the window or the opening to the site of the tube. And the flame safeguard looks for that drop-in signal, and it needs to see that drop-in signal. And if for some reason it doesn't see that drop-in signal after a certain period of time, it will lock out, indicating a scanner failure. So this is very important, but if you have a self-checking scanner, then your application can run 24/7, 365. So the ultraviolet self-checking scanner is extremely important. There's way too many applications out there where people are utilizing the standard UV scanners where they should be using the self-checking scanner. So that's a question to always ask if you're on a job is, this is a non-self-check scanner. You guys cycle this thing, every 8 hours or so. And if they don't, they need to be aware that they could have a real issue on their hands. And of course, these are utilized on medium to large burners and or the light air atomized oil burners. So this is where you would apply those types of scanners. And there are solid state versions of those too, we'll discuss. What are the common problems? Same thing, sighting, vibration, again, can damage the shutter as well as the tube. Temperature, I've seen that many times. And quite honestly, most manufacturers have a temperature recorder inside so they can tell if it's been over temped. The runaway tube firing when it's not supposed to be there. So when that shutter comes down and it's still firing or giving pulses to the flame safeguard knows that we've got a runaway tube and will shut down accordingly. The shutter failure does happen. It's a mechanical device. It's basically a solenoid that is operating that shutter to close off that view, and that can fail also. And age, of course. Again, some of these will run for 10 years, some of them will run 3 or 4 years. Usually a self-checking scanner, the shutter will fail before the tube does if it's installed properly, and will need to be replaced. So having a spare, again, is important on a critical application. Another type of optical scanner is the infrared. Now, the infrared scanners, of course, go way back to the beginning of everything, and you're going to see that these fall usually into that above 1,000 nanometer range. Okay, and it's a very simple element, lead sulfide cell, and these are going to be applied on small to medium, even large gas or oil burners. And they're usually powered with a very low voltage DC. And the cell resistance is basically, that's going to change based off of the amount of IR radiation. So we're going to see a resistance change based off of how much IR radiation we have there. Now, one of the cool things about the infrared sensor is it's basically what we would call dynamic self-checking, and the fact that if it fails, it will usually, and history has proven, it will fail in an open condition. So open circuit is what it amounts to. So that's really an advantage. So we can actually monitor that and tell whether it's operating correctly or not. The most common problems are sighting, temperature damage, and age, but they are extremely reliable as a rule. And again, the key to an infrared scanner operating properly is back in the flame safeguard. Okay, it's going to be monitoring that signal and making sure that signal is moving and moving quite rapidly, so we know that we've actually got true flame and not some refractory that we're looking at there. So this also brings us now to, well, how do we test these scanners? Okay, how do we test the different ones? Well, please don't pull out the cigarette lighter. It's just not a good idea. Everyone's probably done it over the years, but that's not the way it needs to be done. It needs to be done basically with the manufacturer's approved test equipment. And this is something that's important. You're the front line there for your customer and telling them whether or not the product and what you've got there is safe and operating properly. So making sure that that product operates correctly really falls back to the manufacturer's test equipment. And this is a key to making sure that things are right. I've always said, if you take proper notes when starting up a new burner or even operating an old one, record these flame signal strengths, the flame signal strength at pilot, the main flame at low fire, the main flame signal at high fire. Recording these will give us a good idea if we've got something that's aging. In other words, if that signal was, for instance, at an 80 number, we'll just pick that, at when the main flame was at low fire, and for some reason it's around 30 or so after a certain period of time, we know something is aged, something's changed. Is there some material on the sight tube? Those are some things that could really help us determine what's going on. So recording these flame signal strengths, I would recommend doing that every time you go out on to service any type of burner. Now, let's talk briefly about special applications. There's going to be applications where it's a supercritical process and they may want dual or redundant flame scanners. This can be done on certain flame scanners, and certain flame safeguards will allow you to have two, for instance, UV scanners in parallel. They may allow you to have also two IR scanners in parallel, depending on the flame safeguard. And that's good. If you have one fail, then the other may hold you up. Another reason, though, to record flame signal strengths. Usually you're going to have a stronger signal with two in parallel than you will with just one. So that can kind of tell you what's going on there. But obviously in checking out a system, that's where you would want to blind one and make sure that, you know, the signal changes. And but you need to know that you can actually have redundant flame scanners. Now, in certain flame safeguards, you'll be able to add smart or solid state flame scanners. And we can have obviously an and or an or situation. An and where both flame scanners have to be on. We would have those flame on contacts, if you will, in series. We could have an or situation where both those scanners, either one could bring on and say, I've got flame signals. So if your flame safeguard is the type that can actually accept a dry contact input, then a smart flame scanner could be utilized, and you could utilize it in an and or an or application. The nice thing about having two flame scanners sometimes is you can sight the pilot with one and you can sight the main flame with the other, okay? So it can, if you have issues where you can't see both effectively, that's where two scanners can come into play and be a problem solver, okay? Other special applications would be like for flame switches. Sometimes on applications in big process plants, they may have their own combustion control system that they've designed. And this is where you're going to have a simple flame switch. This could be a flame scanner connected back to a flame safeguard that is just saying, yes, I've got flame, or no, I don't. In other words, just used as a dry contact. Or it could be a smart flame scanner that has that built in, okay? So again, just another application of a flame sensor. So we get asked a lot of times, what about reliability? Which one is the most reliable? Well, it really depends on the environment. It depends on what temperature range, you know, that the scanner is going to be in. Depends on how much vibration it's going to be subjected to. And obviously, you know, age comes into play. But, you know, there's a lot of ways to get around a lot of things. For instance, temperature in particular. You know, you can buy heat insulators. You can buy, for instance, unions, in particular, unions that have quartz windows, so you can prevent a lot of that heat from getting back to that flame scanner, which will increase its life. And obviously with vibration, if it's really bad and can't be prevented, fiber optics can come into play. So there's a lot of different things we can do to increase the reliability. Obviously with fiber optics, if you've got a high temperature situation, that can come into play too. There are also products out there called cooling jackets that can use process air or instrument air to actually cool the flame scanner too. So if you run into a situation where it's really unusual from a temperature standpoint, vibration, whatever, you need to contact us and we can make sure that you're get the right product and the right accessories to make it work and be reliable. That is a snapshot, gentlemen, of basically flame scanners, the different types that are out there in the industry, how they actually operate, how they're applied to flame safeguards. And hopefully through this process, you gain some more knowledge of how they should be operated and what to look for when they're not operating properly. So at this point in time, we want to take and review the questions that you've sent in. Okay. Well, I hope this was educational for everyone. I've got, looks like a few questions here. One of the first questions, when a burner is off and you can hear the self-checking scanner making a ticking sound, is that normal? And actually, it can be, because that's usually the mechanical shutter that's actually operating if the power is applied to the mechanical shutter. And that's another thing, a lot of self-checking scanners may have a separate power input for that self-checking solenoid, or so that's something that could be looked at, and you could remove that or apply it, make sure that it's actually operating. Yes, it is normal most of the time. I've got another question here. If I'm having a false flame lockout and I remove the scanner and I can see arcing inside the UV tube, is it bad? Yes, what that really means is probably that tube has lost its seal, and when it loses its seal, just air gets in there and it will just start arcing. So basically it's in a runaway condition, and yes, that tube would be bad. Let's see, we got another question here. If I'm getting multiple flame fails during PTFI, what could be happening? Well, there's a variety of things here. Obviously, during PTFI, if, for instance, the fuel pressure on the pilot assembly is just not quite high enough, that could be causing it to not light properly. And most flame safeguards will look for flame at the end of the PTFI, so it gives that period of time. Although we could also end up with a situation where we get a false flame where the spark is being picked up, and that's where we might want to actually change to an early spark termination flame safeguard setting. One more question here. If I'm having a problem with weak flame signal on a steam atomized oil application, what can I do to correct this? Well, if this is a UV flame scanner, I would suggest, because steam really absorbs that UV, a lot of the UV, and depending on the siting, it would probably, the first move would be to go to an infrared sensor and probably change the amplifier on the flame safeguard or move it over to the infrared inputs. That's some that are right there. Mr. O, were there some questions that you have?
Well, yeah, thanks for bringing me on. I wanted to go back to the question about flame failure during PTFI, because that can be a really difficult thing to diagnose because there's a lot of different things that could be going on. The first thing that could happen is that the pilot flame just may not be coming on, and that's the first thing to look for. The second thing to look for is if the pilot flame is coming on and the scanner isn't seeing it, it could be the location of the scanner and the scanner needs to be adjusted, or it could be electrical noise is interfering with the scanner, because on most boilers, the number one electrical noise generator is the ignition transformer, and it's only on during PTFI. So if you're getting flame failures during PTFI and you can visibly see the pilot flame is there, it's a good idea to go through your checklist of all the things that can be causing electrical noise on the flame scanner.
Exactly.
And you
Yes.
touched on it earlier, take a look at the routing of the flame scanner wires and the ignition transformer wires. They should be a long ways apart. And recall that the ignition transformer makes a circuit from the ignition transformer through the igniter, and then there's a return path for all those electrodes through the burner to the ground. And you got to watch that whole electrode path and make sure that the flame scanner wires don't cross it, because the igniters are grounded through the burners 9 times out of 10.
That is an excellent point, and quite honestly, something I should have stressed more during the presentation. like on flame rods, some people have issues with flame rods not detecting the flame, and because it's using the burner as the ground, on that application, if the grounds have gotten corroded or whatever, that can be the problem right there. And quite honestly, grounding on any of these systems anymore, because they're microprocessor based, checking grounds is one of the first things I think anyone should do, regardless if there's issues.
They used to make those 10,000 volt ignition transformers, and those grounded to themselves, right? But nowadays, all you ever see are the 5,000 volt or 6,000 volt ones, and they all ground through the burner, right?
Well, that's what I've seen is for gas applications. Yes, the higher voltage ones, of course, what I think, and again, this is, I haven't dealt as much with oil as you have, but I think those were like double-ended, and I think those were actually internally grounded some way. But you're right. It all goes back to if it's not grounded properly, that voltage has got to go somewhere, and it's going to find something to damage. Anything else? Well,
Could well, what do we got? We have 4 more minutes till we're up at 3 o'clock. Could you talk more about saturation? Because this is something I just learned about relatively recently. I was starting up an oil burner, had a beautiful flame, um, started it off, started working my way up to higher and higher firing rates with a good flame signal and a good looking flame. Everything looked fine, and then at about 30 or 40% firing rate, I was dropping out on flame failure. And it did it 2 or 3 times at the same firing rate, and my flame signal looked great. I mean, it was maxed out. I had nice, clear, bright flame. There were no red flags, and and then I called into preferred tech support, and they introduced me to the concept of saturation. Can you
yes.
go into that a little bit?
Sure. Saturation most of the time will occur not so much with UV as it will with infrared type scanners, but what it amounts to, quite honestly, is you've just got so much signal that it's overloading the front end of the flame safeguard. And in particular with infrared, if it's so massive, it becomes a signal that it can't see the fluctuation. And then it needs to see that amplitude fluctuation to know that it's truly combustion or flame versus refractory. And there's ways of really correcting that. The most simple ways people have used in the past have been orifice plates that you put in front of the scanner itself. And the orifice plate being a small pinhole, and so you don't have full view. And that actually works quite well in a lot of applications. Now, obviously, there's other ways of doing it. There's what we call filtered glass, if you will, or quartz for like UV. So you can actually buy that in percentage and drop down that signal also, so that you absolutely, don't overload the front end, because that's what's going on. It's such a high signal that it can't discriminate, and that between, what's real combustion and something else.
Yeah, so in that situation, I was using an IR scanner, and
Mm-hmm.
the solution that preferred tech support recommended to me was to take a piece of sheet metal, drill an 1/8 inch hole in it, and then slide that between the scanner mounting swivel and the burner, and
Yes.
make the scanner look through that 1/8 inch hole. And
That,
I was very skeptical because it's counterintuitive, right?
yes.
You're tripping off false flame, so obviously you don't have enough flame signal, right?
Yeah.
Orificing down the flame signal seemed like the wrong way to go, but it worked perfectly. And then they explained to me what you just explained, that the scanner is looking for flicker, and if it gets too much signal, it just doesn't see any flicker, and it thinks it's seeing hot refractory, right? And it's
Correct.
programmed to shut you down.
Exactly. And like I say, that's one of the issues that, quite honestly, is most of the time solved fairly easily. But I've actually done it in my past, not only on the standard like UV or IR scanners, but I've even done it on the more expensive and elaborate smart scanners. That sometimes the simplest solution actually will work. So, but very good question, and that's people will run into those issues occasionally.
And it's a hard thing for the technician to diagnose because it's so counterintuitive. I'm failing a false
Really
flame because I've got too much flame signal. So
exactly.
it's just something for technicians to be mindful of.
Absolutely. Anything else that we've got? Well, everyone, thank you for attending today. Hopefully this was very educational for you, and don't ever hesitate to call us. We want to help if you run into issues, or we can help you with any of your combustion needs. So thank you for attending, and have a great rest of your day.